Yeah, so the first question's a bit weird because it's specific heat capacity, and I think you get slightly different answers depending on what book or website you're using. So like I think in chemistry, in chemistry they're more prone to use grams. So for me, specific heat capacity would have been the energy required to raise 1 kilogram of a substance by 1 Kelvin. But I can see on this chemistry website they have 1 gram and 1 Celsius. So I'd have to look up past marking schemes to see which one the leaving cert wants for this. Um, yeah, so this one also says unit mass, and a unit mass in physics, the SI unit for mass is kilogram. Yeah, actually, this is a nice little table. Yeah, kilogram. Good. Yeah, I like this website. I'm going to take this table. Um, that's very nice, actually. Little table for the first question. If you want to pause it and have a read through it, that's great, actually. That should be a capital K, and there should be a space there. It's not perfect, but still great, though. Okay, great, great, great. Um, calculate the highest temperature the water could have reached. Okay, let's do the calculation now. All right, all right. So you got 750 liters of water at a temperature of 4, and it rises to, let's say, X. So the energy gained by the water, that's mc delta theta, that will equal, this is for the water, that will equal mc delta theta for the stones. So 750 kilograms of water, and the heat capacity, should we use 4181? 4180 for this one, okay. And it rises from 4 to X, so that's X minus 4. 50 stones, an average temperature 280. And just be careful with the K here, it's kilo, so that's 8,500. Oh, what's the mass? Oh, no need for the mass because it's heat capacity, not specific heat capacity. So it's 50 stones, and each stone has heat capacity of 8,500 joules per Kelvin. And how many kelvins are there, or change in Kelvin? It's 280 minus X. What's a sensible answer before we calculate it? I guess they're trying to boil the water. I think the question will get a bit complicated now if we get an answer more than 100, because then we'll be dealing with steam. I hope they don't do that. I'm going to hope that the X comes out to be some number like 85. Let's see. 750 times 4180. So that's 3135000 minus 12540000 equals 119000000 minus 425000x. I'm sorry, I left out an x here. So let's see, 3135000 minus 425000. So taking the x's to the left, 2710000x equals 1190000 plus 12540000. 131540000. Oh, good. Not as high as I guessed. X is 48.5 Celsius. Or 322 Kelvin if you want it in Kelvin. That's the highest temperature could reach, assuming no heat loss. How could you improve the design of it? I don't know. I think what might be missing is some kind of cover, a wooden cover that they can pull over it to keep the heat trapped in. That'd be my guess. So I'm going to say a removable wooden cover, i.e. a lid, so to speak. Yeah. Okay, I think that's okay for that part. Okay. Next. Stretch string at the third harmonic. Okay. Let me just draw the first harmonic. I work my way up. So the first harmonic would be this. That's the first harmonic. Which, by the way, is half a wavelength. The second harmonic would be 1 wavelength. And then the third harmonic would be 3/2 wavelengths. So that would be, oh yeah, it's a standing wave, so I should complete the diagram. So then 1.5, okay. And then here we go. And these points here are the nodes. And then these points, that's the antinodes. Okay, draw a label diagram, stretch string vibrating at its third harmonic. A 65 centimeter string of mass 0.21 grams is stretched between 2 points, which are 34.1 centimeters. It is required to vibrate at its fundamental frequency of 440 Hz. Calculate the tension that is applied to the string. Oh, I definitely don't remember this formula. It's one of the formulas I don't remember. I'll have to look it up. One moment. Okay, got the formula now. I couldn't remember the exact position of everything in the formula. So it's 1 over twice the length, which is 0.65, root the tension, which we don't know, and the fundamental frequency is 440. A 65 centimeter string of that mass stretched between 2 points, which are 34.1 centimeters apart. Okay. Oh, wait, is the L the length of the string? One second. I think actually the I'm not sure if that 34.1 is needed or if it's a bit of distraction. And then the mu is the mass per length of the string, mass per unit length. So the mass is 0.21 times 10 to the minus 3 kilograms over 0.65. So let's do a bit of cross multiplying. 440 times 2 times 0.65 times root 0.21 times 10 to the minus 3 over 0.65 equals root t. So I got a tension of 106 newtons, the three significant figures. Let's double check that. Yeah. Determine the frequency of the string if the tension is now reduced by a factor of 4. So in the formula, if you divide the tension by 4, what would happen to the frequency? It would, yeah, so the frequency would be 1 over 2L root T over 4 over mu. That's the new frequency. But 1 over root 4 is 1 over 2, so that'd be 1 over 2 times 1 over 2L root T, the old tension. Yeah, it'd be halved. Yes. Something's not settling right. I just never used this. Oh, they tricked me. Oh, those sneaky. The string is 34.1 centimeters. It's stretched to 65. So when they said a 65 centimeter string of mass 0.21 grams is stretched between 2 points of a lyre, which are 34.1 centimeters apart. Oh man. It's terrible. Because I'm not. Is the string 65 centimeters or is it stretched to 65 centimeters? And how could it be stretched if the distance is only 34.1? Wow. I need a diagram. I don't know what they're trying to say here. A 65 centimeter string of mass that is stretched between 2 points of a lyre. I'm gonna need a picture of a lyre. This is terrible. What a terrible situation to be in the exam. You know, I found the picture they were looking at. And now I'm not so sure about what's going on in this question. So you could have a 65 centimeter string, but then it's wound up, it's stretched. I mean, what a terrible question. What a terrible question. The earliest harps and lyres were produced in the Bronze Age. Different strings in a lyre may have different lengths, okay, different tensions, different diameters. A 65 centimeter string is stretched between 2 points of a lyre, which are 34.1 centimeters apart. So, if they're just winding this around and stretching it, the excess string doesn't enter the situation because it's just tied around the top. Oh, I hate this question. It's terrible. So I think now, in hindsight, I'm going to have to change those numbers to 0.341, 0.341, 0.341. 440 times 2, that should be 341 as well, times 0.341. But actually, no, that one's not 341. That one is still 0.65. And then square the answer. So the tension is 29 newtons. So that length there is the length of the string. We have 34.1 centimeters of string, but that's the mass per length of string. So I still need the 0.65 there. Yeah, 29 newtons. Okay, now I think this part is finished, but man, I hate this question. Okay, let's have a look at the last part. What are isotopes of carbon? So these are, an isotope of carbon has 6 protons, but a different number of neutrons. So what are isotopes? So isotopes are just elements that have the amount of neutrons in them change. So for example, carbon-14 has extra neutrons in it, but they still have the same number of protons. So the ratio of C14 to C12 in the sample is found to be 1/4 of that of a living tree. Is this artifact from the Bronze Age? So what's going to happen is the ratio C14, okay, carbon-14 decays. So you start off with 100% carbon-14, and then after a half-life, you'd have 50%, and then after another half-life, you'd have 25%. The ratio in the sample is found to be 1/4 the ratio found in a living tree. Okay. Oh, okay. So I'm not sure what the natural ratio would be to begin with. So like you could have something like 1 part carbon-14 in a living tree, and then X parts carbon-12, and then later, so this would be 1 to X, and then later you have 1 part carbon-14, Y parts carbon-12, 1 to Y. Well, this is 1/4 of what it was. So I think that's making it sound like 2 half-lives. And that half-life is 5,730 years. So 5730 times 2. That's 11,460. So that's around about 10,000 BC. I think it's before it, but I just want to make sure I'm not messing up anything with the ratio stuff. So let's just keep it simple. Let's say we have 1 kilogram of carbon 14, and I know this isn't real numbers. Just pretend it's at the beginning. A living tree starts off with equal amounts. Then after one half-life, carbon 14 decays, so you'll have 0.5 kilograms of carbon 14 and then 1.5 kilograms of carbon 14. So here the ratio is 1 to 1, and here the ratio is 1 to 3. And then you'd have a 0.25 kilograms of carbon 14 and then 1.75 kilograms of carbon 12. That's 1 to 7. Okay, so it's not quite 2 half-lives actually, so the ratios tricked me. So it's a little bit more than 1 half-life. So it is between 1 and 2 half-lives. So therefore Bronze Age. So that's what is it now? Yeah, about 5.7. So that's 11460, 5730 to 11460 years ago. But it'd be nearer to the 5730. I wonder if we've calculated exactly. Because I feel like the maths would be a little bit tricky to calculate. And by the way, I don't think it matters what the initial ratios are. So for example, if you have carbon 14 and carbon 12, let's say it's mostly carbon 14, like 10 kilograms. And here carbon 12 is 1 kilogram. After one half-life, that'd be 5 kilograms and 6 kilograms. Then after another half-life, 2.5 kilograms. 2.5 to 8.5 kilograms. So the ratio would be 10 to 1, 5 to 6. So that'd be 1 to 0.1. And that would be 1 to, what's it, about 1.2? Oh, maybe it does matter. Okay, I'm going to need to think a second about this last part. Yeah, my mistake. I got confused on this last one. I was just looking up, and then it dawned on me. Carbon 12, of course, is stable because that's 6 protons and 6 neutrons. What I was thinking incorrectly here, I forgot that carbon 14 decays not to carbon 12, but to nitrogen. So the purpose of having carbon 12 in this question is to be a reference point. The carbon 12 is fixed, it's stable. It's the carbon 14 that's decaying. So when they say the ratio of carbon 14 to carbon 12 is found to be a quarter of what it was previously, basically what they are saying is that I was right the first time. It's 2 half-lives. So that's like more than 10,000 years ago. So I'm going to say that's pre-Bronze Age. I think so. Generally, this whole question, I'm just not happy with. Well, that to be fair, that last part I kind of screwed up a little bit. That's on me. But the previous part about the layer, I think that's on them. But that's my opinion, anyways. I wonder what you think.